Welcome to episode 5 of the Ultrasonic Sensing video training series. This video will discuss the various analog front-end receiver configurations available for the amplification of received ultrasound energy. The block diagram of an ultrasonic sensor system can be simplified down to two primary blocks, the driver and receiver. The receiver block includes the analog front end, or AFE, to amplify and filter received ultrasound energy. The AFE is designed to condition received ultrasonic frequency signals from a few microvolts RMS to tens of millivolts RMS. The received echo is first amplified with a fixed gain low noise amplifier, followed by a second amplifier stage which may be another fixed gain amplifier, a programmable time varying gain amplifier, or a logarithmic amplifier. The low noise amplifier, or LNA, is a single-ended input non-inverting amplifier with a low fixed gain output. As the first stage of the AFE, the device implements internal protection from the large driver voltages reaching upwards of hundreds of volts during burst. AFE protection from these large driving voltages is typically dependent on the external AC coupling capacitor to limit current flow at the input pin. In addition, the external capacitor network for the receiver is used to provide high-pass filtering to remove 1/F noise and DC offset. The variable gain amplifier in the AFE implements a time-varying gain feature which allows the user to set different static gains and also specify a gain profile for the echo listening process over the record time. This feature allows for uniform amplification of echo signals from objects at different distances without saturating the amplifier output. As an example, for closer objects, gain can be programmed lower initially in time and then increase during the recording time to detect farther objects which have a very small echo signal. This feature helps in attaining sufficient SNR after ADC conversion for all distances for accurate time-of-flight measurement. The time-varying gain parameters are typically stored in a device memory and characterized by the initial fixed gain parameter, a time-varying gain start time value, and an array of 5 gain-varying cross points. The time value, or TVG start time, is expressed in terms of absolute time, and all following TVG points are expressed as a delta time between the current and previous point. All gain values are expressed in an absolute gain value in dB and are unrelated from each other. The final gain setting of TVG.5 will be kept constant until the end of the echo record time. A linear interpolation scheme is used to calculate gain between two TVG points. The TVG gain resolution is 0.5 dB typically. Given transducers are high Q components, a bandpass filter, or BPF, is required in the AFE to limit the bandwidth of the AFE to only further amplify a narrow frequency range centered at the transducer's resonant frequency. The BPF is able to reduce noise from the LNA stage and external noise sources. In the case where the Q of the BPF is constant in a device, such as the TUSS44X0, the bandwidth increases as the center frequency increases, resulting in an increase of integrated noise. And the TUSS44X0, using the alternate high-pass filter, becomes favorable for center frequencies above 500 kHz to limit the amount of 1/F noise. In the case of the logarithmic amplifier, or a log-amp, the signal is first bandpass filtered to remove noise outside of the transducer's signal band, then enters the log-amp for input-dependent amplification. The log-amp enables high sensitivity for weak signals and a wide dynamic range over a full signal range without causing saturation of the AFE. Log amps are used as a form of automatic gain control in applications requiring large dynamic range of operation, fast settling time, and high bandwidth, such as an ultrasonic sensing system. The TUSS44X0 implements a demodulating type of log amp to calculate and detect the logarithm of the input envelope signal. Here we are comparing a log amp AFE to a TVG AFE. In this case, the IC is coupled with a 200 kHz transducer and used to detect two different objects, a 7 cm diameter cylindrical metal pole and a flat 24 by 32 cm metal sheet, placed at 30 and 63 centimeters at separate times. figure shows the output voltages during these measurements. The transducer is excited with drive pulses at 20 volts, which saturates the AFE initially. The second peak at the output occurs when the reflected object echo is detected. Since the reflected echo strengths vary depending on the object's shape and distance, the strength for the sheet is larger than that of the pole by a factor of 3, and the strength at 30 centimeters is larger than that at 63 centimeters by a factor of 4. However, the peak amplitudes do not scale accordingly due to the input level dependent amplification of the log amp, preventing saturation of the AFE while keeping enough output SNR for reliable detection. Furthermore, the pedestal level, or noise floor, is constant across time. As a result of this, a fixed threshold level for object detection can be set just above the pedestal level without a need for manual gain or threshold level calibration. For comparison, similar object detection measurements are performed with a TVG-based system, which provides an ADC output and has a noise performance comparable to the log amp-based one. The figure shows the ADC output when a constant gain of 58.5 dB is applied to be able to use a fixed threshold level across time for simplicity. Two problems are observed in this case. The sheet at 30 centimeters saturates the AFE, resulting in a loss of amplitude information, and the pole at 63 centimeters yields peak amplitude very close to the noise floor, preventing reliable detection since this will require setting a threshold too close to the noise floor that may result in false detections. To compensate for these small peak amplitudes at long distance, TVG is applied to increase the gain from 46.5 to 74.5 dB over time as shown in the figure, enabling the ability to apply a threshold level at 63 centimeters for the pole. But the rising TVG profile creates a rising noise profile, causing a need for a time-varying threshold. Both time-varying gain and time-varying threshold require application-dependent manual calibration and thus additional processing. This is a big disadvantage compared to the log amp-based solution. In summary, the log amp simplifies the system design by offering use of a fixed threshold level and automatic amplitude scaling independent of distance and object shape. Use a log amp when your system needs to detect a variety of or unknown target types, and use a time-varying gain for a group of predetermined or verified target types.